Pat. He probably needs no introduction, since he's one of the founding members of this festival. So I think he might also be the only one to have attended all the talks for the 12 editions. I'm not saying anything to anyone. So Pat has taken a number of positions, in major institutions around the world, etc. He's headed some theory departments around the world as well, but he is most well known for his undying love of cats. And he has very smart cats. And if you don't know it, you should probably read one paper. He's the co-author of one of his cats. And last but not least, we're kind of happy to have him in person, because there are precedents that, cats need nurturing. So we're very happy that you're not at home nurturing Geronimo, and you're actually with us, in person. So thank you for that.
It's an appropriate introduction, the emphasis on the important things. Yes, it's a pleasure to be here. It's nice to get out of jail. So this talk is about a subject a little bit different from my usual. It's on scrape-off layer broadening. It really deals with the issue of entrainment, is how the human race calls it, or turbulence spreading, which is how we call it. And it spans a list of ideas from people ranging from Goldston to Goldenfeld. And so we cover the bases of the sublime and the ridiculous, and I let you figure out which is which. And many collaborators, some overlap with George's, but I particularly want to mention three young people, Shu Chu, Ting Wu, and Ting Long, the latter two from SWIP. And Shu Chu was actually an undergraduate at the Chinese Academy of Science University in Beijing, and we did all the portion of this work entirely by Zoom. I never actually met him face to face yet. He's now in Princeton, and we have acknowledgments from many people, particularly Professor Goldston and George and Jose Boedo also. So I was warned by our commander to keep this, try to keep this accessible to a broad audience, and I appreciate that problem. So I start with a bit of a brief primer on the edge and scrape-off layer. And some of this you heard, but never hurts to hear it again. And it'll be a little bit of a different take. And I'll give history. I think it's very useful to understand kind of where we are on some of these things by looking at the history. And of course, my history is a bit different than the Becquelet performance last night, as you'll see. Then I'll talk about the soul width problem and how it presents a kind of a very different plasma boundary layer problem than what you find in Landau and Lifshitz say. Then we'll talk about kind of a theoretically motivated data analysis exercise, looking at something called the turbulence production ratio. And the idea, basically, we show that most of the turbulence in the scrape-off layer in a garden variety state is in fact driven by spreading and not by local production. So that's sort of item number one. Secondly, for the H-mode case, where the turbulence production in the scrape-off layer is killed, leading to major problems. One is interested, if one had a turbulent pedestal, how far the turbulence could penetrate in the scrape-off layer. So that's a problem in turbulence spreading. So I'll talk about how the analysis of that. And then these motivate a closer look at turbulence spreading, back to more fundamental things. So in the style of the festival, this talk is backwards from maybe what I'm sure Oscar out there is very unhappy, because we're starting really almost from the engineering problem first and heading toward the more fundamental physics at the end. But nevertheless, I think it's useful to approach it that way because it illustrates how dealing with the realities of the the tokamak confinement problem drive you to understand better the fundamentals, which is a logic that I think is lost at times. So all confinement devices have an edge. Very important, simple point. Otherwise, it's not a confinement device. And they all have a scrape-off layer. So you've seen this picture, the cross-section of the donut, the confined plasma. You have the separatrix bounding the confined plasma, and the field lines cross at the next point. And then you have a region around it, which constitutes a boundary layer, and this is called the scrape-off layer. And this whole thing is encased in the vacuum vessel. And the heat that and other things that come out of the main plasma, it runs along the field lines to the plasma facing components. And this is a diverted plasma. And the reason it's called diverted is the magnetic architecture diverts the point of contact with the boundary away from the proximity to the main plasma. In the good old days, there was no diverter, and there would be something called a limiter, which would be a piece of metal stuck somewhere, and that literally would scrape off the plasma and the layer of plasma around it, thus got the name scrape-off layer, if you're wondering where that came from. And that, of course, was idiotic because you're putting the contact with the metal surface right up against the plasma, and you have impurity and all sorts of other things, wonderland. One other thing which wasn't mentioned, these pictures are deceiving, and the magnetic field lines are still primarily toroidal. So they're out of the plane of the paper with a slight downward tilt. One very important point is that in a power balance, all the heat that is input or generated in here ends up in this small region of the plasma facing component. And that is an extremely challenging issue for a number of reasons. So this is about a turbulent boundary layer problem. Now you've heard about the L mode and H mode. So very quickly, L mode looks like this. H mode is a steepening, a strong steepening of the profile gradients in the vicinity of the separatrix, but inside very clearly, a strong shear layer is formed by Reynolds stresses, by feedback through the pressure gradient and diamagnetism. This leads to a turbulent quench and a transport bifurcation. So if you plot Q versus minus grad T, heat flux versus minus grad T, it's of course, it exhibits a bifurcation, a kind of S-shaped curve kind of thing. There is a threshold for this to occur, and making the, again, a point of disagreement with last night is achieving the power threshold for ITER is quite non-trivial. That's, I think, the game is far from clear there. Another point you should get from this talk is that bad things come with good things. So in addition to the improved confinement, these steepened gradients near the edge lead to MHD type events, which are called edge localized modes. And okay, that means they're modes near the edge. And the word elm is a pun. It comes from St. Elmo's fire. Okay, so these look like bursts at the edge, and the fellow who discovered this, Fritz Wagner, had a sense of humor, and unlike most of the leaders of this program, and he dubbed the thing Elm, and with the idea of the Elm fire. And these events are very complicated, but they do seem to have some correspondence to sort of garden variety MHD instabilities you might calculate from energy principle in an elementary and MHD course. The difference, of course, being hideously complicated geometry, but that's what computers are for. It's important to have the point that, of course, the good confinement of the H mode is what uncovered the proximity to the stability boundaries for these things. Now, for the soul, you have open field lines, and you have divergence of Q or gamma equals 0. So you balance perpendicular transport, which is, of course, it's not diffusive, as we'll see, but this is how it's thought of. So you have to start there. And parallel flow at the sound speed, and a perpendicular wavelength of the scale length of the scrape-off layer, and a parallel wavelength of a connection length. And these two together, there's a missing factor of C sub S there, define the balance of perpendicular and parallel transport. And this defines the crude soul width that we saw the other day. And the idea here, this D is thought to be a D due to some instability that occurs locally in the soul. I should say that in not all cases is the parallel transport sonic. In the important case at high density, it becomes conductive, which then couples the density to the soul width, and at high density, you broaden the soul. And this is relevant to density limits and other things, which we'll come back to. But it's this sort of interplay that defines the width of the heat load on the plasma facing component, which is an important issue. So this, this is, what's the literary critic Frederick Jameson has a saying, always historicize. So I think it's good to put these things in a historical sense. This is my incomplete cynic's history of magnetic fusion. So it was declassified in the mid-50s. Amazingly, no indictments were handed down. In the mid-60s, we had the field had the famous exercise of Trieste with Rosenbluth and Sagdayev and Kadamtsev and René Pela and others, all of whom were unmentioned in last night's circus. And much of the basic physics of tokamaks were worked out then. In the mid-70s and continuing into the mid-80s, we really entered the hero of the great leader. And this was evident. This one manifestation was the declaration of victory from Princeton when they got their beams working on PLT. But the euphoria didn't last long, and the quick march to Marengo really developed into the retreat from Moscow into the mid 80s, when the great leaders, you see some familiar names. He wasn't mentioned either, which was interesting. Anyway, the great leaders discovered that the energy confinement was degrading with input power, and they were basically getting nothing for all their beams. And a really major step forward, which arguably is why we're still here, which is, by the way, occurred in 1982 with the discovery of the LH transition on Azdex, a tokamak in Germany, now reincarnated in Chengdu as HL2A. And this was really due to the efforts of Fritz Wagner. And this is this spontaneous transition to high confinement and the edge transport barrier. And by the way, along with this discovery, Wagner, he identified ELMS, he got the basic physics, not very quantitatively, nothing fancy, and he understood the implication. And the key to this was control of the boundary. In other words, not doing stupid things like a limiter. And I should say that Azdex was one of the first diverted tokamaks, and that's what the acronym means, axisymmetric diverter experiment, right? And there was there was an identical experiment at Princeton who missed all this. So in the 90s, we came a lot of noise about internal transport barriers, which I think are at the moment something of an evolutionary dead end with a possible caveat. Some of us spent a lot of time on all this. The 2000s, as sort of ether started to loom, there was rising concern about this issue of elms and their effect on the plasma, the plasma facing components. In other words, you would get these bursty relaxation events, which would dump all the heat into those relatively narrow diverter plates. And this became then a subject of great concern and motivated gains at elm control. But then around 2012 came a set of scaling studies and the Goldstone heuristic drift model. And it showed in the regimes of relevance, and we'll come to this, the scrape-off layer width is actually scaled inversely with current and was a lot narrower than they thought it was. And this, I think, was a kind of a major bolt, because it's saying even absent the elm, even, with the baseline heat load issue was a problem, right? Because the distribution of the heat, as you will see, was far too narrow. And then we had a talk at the TTF meeting in Transport Task Force in 2013 by Kikuchi-san, another one of the great leaders. And this was interesting to me. There was a lot of wine served at this meeting. It was in Sonoma, California. And the thrust of it was the conflict between good confinement and good power handling. And in particular, he started to advocate getting rid of H mode and considering a different confinement regime. So, it didn't take long for the thing that saved our neck now to be suggested to be thrown out the window. If we look into the present day, I would say the focus of the program is on these trade-offs between confinement and power handling. These issues are at center stage. These sort of enhanced confinement regimes now, but with a turbulent edge, are the thing of greatest interest. With the grassy elms, the wide pedestal QH mode, I mode that we talked about, RMP, negative triangularity, which is alleged to achieve H mode-like confinement without a transition. One wonders what happened to ITBs in L mode edge, but never mind. The other interesting thing is in machine design philosophy. In the good old days, you would design the core and then just try with whatever space you had in the vessel to clean up the mess, to hold what came off. Now you're heading toward much more of an integrated design, and in fact, maybe more an integration inward, where you design the boundary and the diverter first, and then ask what kind of core can I live with in that. So the arrow of the design evolution has changed. The message you should get is that edge and boundary physics has been the center of the action in MFE since the 1980s. It is the absolute key thing. So at this point, one would like to have a color picture from simulation, but since I wanted to have a color picture that had some physics content, so I chose this color picture, which I think you're all familiar with. And really, this is all you need to know to understand this stuff. But you'll see that as it goes along. So now we come to the scrape-off layer. The conventional wisdom of the scrape-off layer, which you can find in Stangby's book or a bunch of others, I won't name them since we have one war going with Russia at the moment. I think one's enough. Is really that the scrape-off layer is a boundary layer a la Blasius, but with a turbulent diffusion coefficient, and the turbulent diffusivity is due to some zoology of localized instabilities in the scrape-off layer, and you proceed by familiar quasi-linear techniques. One thing that this ideology overlooks is the phenomenon of intermittency, which George mentioned, is that part of the boundary layer is also home to the production of these localized strong perturbations in density and other things, but density is what you measure most easily, called blobs. Physics of blobs, you can think of them as localized high-density perturbations that propagate. And the physics of blobs is extremely important, and you'll hear more of it. So this is the way the scrape-off layer was handled. And there was precious little done to answer Norman's question of the other day of actually looking at kind of, trying to look at the theory experiment connection, for example, and the validity of that expression. So along came Professor Goldston, and the sad part of the story begins. And well, the basic point is he very much appreciated the scaling study by Brian LaBombard of H-mode edges. And the thing that this showed was the width of the scrape-off layer was scaling very strongly with current. And those of you in this business know when you see a strong inverse scaling with colloidal field, that reeks of neoclassical processes. And Rob jumped on that, and he noted you could build a simple phenomenology of take the curvature drift or grad B drift in an inhomogeneous field, and take the finite dwell time for the parallel streaming, put it together, and you get a scale length. And this scale length is the width of the soul, epsilon rho theta ion. So that's the colloidal ion gyro radius with the colloidal magnetic field. And it turns out this becomes a pretty good fit to the H-mode soul width. Now, there's a few comments on this. Number one, it's pathetically small. And again, in taking issue with Becquerel, I mean, size does matter on these things. And not only is it pathetically small, but in fact, the usual logic of build a bigger machine and it will get better does not apply here. In other words, size does not matter for the scrape-off layer width, right? You'll know no scaling with major radius and so forth. The other thing is what you usually want for good confinement is a lot of current, and that you're going to pay for that by making the scrape-off layer even smaller. And this expression works pretty damn well. So there's a famous plot from Brunner, the Brunner paper 2018 of lambda Q versus the colloidal field. And you see all the relevant devices have their representatives on the plot. I don't see any points from West. And, but down here at higher colloidal field, we're talking about lambda Q 1 millimeter across, right? I mean, that's really bad. And, it's a pretty good fit, okay? So the message is that the heuristic drift model, these were all H-mode discharges, so that, it works well in strong H modes, and it's bad news. So why does it work well? Right, is the relevant question. It works because the E cross B shear suppresses the soul turbulence. I mean, you could go back to this idea of the interchange as the soul turbulence mechanism and bring the E cross B shear stabilization. But you have to realize the interchange drive is related to the soul width through, as the gradient scale. But the E cross B shear has a stronger dependence on the soul width because the edge temperature sets the potential. Then to get the shear, you have two factors of the soul width. So for lambda squared narrow, this guy wins and just wipes out the interchange instability. And bingo, you have a nice stable edge or soul, which leaves only neoclassical, this kind of neoclassical scrape-off layer width, which is pathetically small. So this, as I said, is now really, it's on everybody's short list of the top 5 problems with in ITER. One is the soul width, one is the disruption, one would continue to be elms, and I guess there'd be a few more. But it's really an existential problem, and it typifies these trade-offs between good confinement and good power handling, and the fact you may have to give up some confinement to handle the power. And this has driven now a focus on turbulent boundary states with improved but imperfect confinement, and these various acronyms that I mentioned. The other thing now is that in the assessment of any performance of a regime, the scrape-off layer width is now a key part of the story that has to be addressed. There have been computer simulations always with very nice color pictures that I'll spare you that have the message of go to ITER and all will be well, but they really don't address the physics and discuss how this miracle is going to take place. So the first thing is maybe to look at what's going on in a simple boundary layer, and is this idea of production of turbulence by local instability, does this have any content whatsoever? And then the next step after that is, if you have a laminar boundary layer that's stable, could this be penetrated by turbulence coming from the pedestal? So but step one is a kind of a simple study. So, the classic flux-driven boundary layer problem that you might find, say, in Landau and Lifshitz, you have a heat flux from a surface, you get the height to the 1/3 scaling, you have plumes and all, and you get a kind of the standard story. I mean, plumes, plumes, blobs, etc. If you try to adapt this to the scrape-off layer, well, one is you have these open field lines. The other thing, of course, is that you don't have a plate, you have a turbulent edge. So you have energization of the boundary layer due to both the heat flux and the flux of turbulence intensity coming from the edge region into the boundary layer. And this is the beloved phenomenon of turbulence spreading. And you could include the blobs game as an intermittent version of turbulence spreading, which is, by the way, Peter Mons, who was here earlier, wrote a nice simulation paper on the connection between the two. So it's really, for the golf fans in the audience, it's a bit more like the problem of energization of the boundary layer by turbulence rather than generation of the turbulence by an instability. So you have this phenomenon of turbulence spreading or entrainment possibly invading the boundary layer. So then you have local production and you have energy influx. Who wins? So it's convenient to define a production ratio, which we'll call R sub A. We have RA, but I realized RA was a symbol that was taken for other things. And one of the most basic questions is the soul usually dominated by spreading, or is it dominated by local production, even when it is turbulent? And the latter is the conventional wisdom. And then, of course, comes the issue of penetration. And then finally comes the question of E cross B shear and role of structures. So basically, you do an experiment. So this was done by Ting Wu at SWIP. This was her PhD. So you basically measure and characterize the turbulence energy in the vicinity of the last closed flux surface. And you want to determine this thing, the production ratio, which is the ratio of spreading through the last closed flux surface to local production. And you want to look at the trends in the heat load width, the lambda Q, and the production ratio versus E cross B shear and blob fraction, right? So, and so this was done on HL2A limited ohmic plasmas. These are classic boron plasmas. They still have a scrape-off layer. These were done with probes, basically at the slightly into the plasma at the outboard midplane, and the sheath transmission coefficient was used to help calculate the parallel heat load, and there was a modest database of garden variety omics, which you will see is 4 parameter subgroups, and they're all basically the same, except keep in mind the black triangles are different. And the reason they're different is there is a somewhat significant GAM activity in the cases of the black triangles, and the GAMs are, shall we say, another way to say an edge shear flow, so you have a stronger E cross B shear, certainly not an H mode. The scrape-off layer widths in these are much bigger than the HD, except for the strong shear case, which is still bigger, but not as bigger. So you start looking at plots. So simple thing is to plot the scrape-off layer width or the heat load width versus N tilde over N at the last closed flux surface. So then you see, of course, that you have the heat load width broadens with the intensity of the turbulence. And you also see that the strong shear cases with lower N tilde over N have the lower heat load width. If you plot the heat load width versus the magnitude of the E cross B shear at the shear layer, which is effectively right at the last closed flux surface, the heat load is broader for the weak E cross B shear and narrower for the strong E cross B shear. You'll note there's a bit of a gap in the points, reflecting, of course, the difference, the set with the GAMs and the set without. So that's item number 1. Item number 2 is you can do the same kind of plots of the heat load width versus the particle flux or the diffusion. And again, the heat load width increases with the flux and the diffusion. Again, you'll notice the smallest heat load widths have the least diffusion and least particle flux. There is a hint of a possible saturation here. It isn't clear, okay? So that's one thing, but then what about the spreading? Well, one advantage of this is you can actually calculate the spreading with linear probes pretty easily. So this is, you might call it the internal energy density flux. So it's basically the correlator of E radial with N tilde over N squared, and there's a factor of CS to make it an energy density. And you get a plot of lambda Q versus the energy density flux at the last closed flux surface. And this starts to get very interesting, right? So this is perhaps consistent with the expected trend of an expanded scrape-off layer due to increasing spreading across the last closed flux surface. Now, all that is all very nice, but people say, well, it's coincidence, not causality. So you have to address something called the production ratio. So this can get hairy. So we chose the simplest possible thing. This harkens back to something we did with TS some time ago, but is a little different because we avoid using the linear growth rate. I think it's a step forward. So you can, write down a one fluid model, and you have to take care, harkening back to David's lecture, to deal with perturbed pressure balance, because of course the relevant instabilities are incompressible. And if you're not careful with that, you will find stupid things like an apparent acoustic energy flux across the separatrix, which is nonsensical because you're on time scales that are long compared to a magnetosonic time. And you could eliminate all that by just taking the curl and working with the vorticity equation, as we always do. But there's some convenience here to keeping the work with velocity. So, but it's, as long as you keep track of that, everybody's happy. And then you can form the expression for the kinetic energy at in the scrape-off layer, which is the integral of the divergence of the energy flux from the scrape-off layer, from the plasma into the scrape-off layer, and the total integrated production in the scrape-off layer. And the integrated production is, shall we say, the interchange drive, and minus the Reynolds work, which in the cases we were considering, this just was a feeble non-player, but in principle, could be important. This of course would drive the zonal flow in the scrape-off layer. And you might ask about the interchange production. Obviously, it's really the curvature times the flux of pressure, but you cannot measure the temperature, particularly the ion temperature, so easily with probes. So for making contact with the experimental data, we wrote this as G C sub S squared times the particle flux, which is a necessary approximation to make progress. So you do all this and you end up with the total rate of change of energy in the soul as the contribution from spreading across the last closed flux surface and the integrated production in the soul. And with the approximations, everything left can actually be addressed by measurement. So you do all that and you define the production ratio, which is this goodie. Right, so this is the ratio of the flux of turbulence energy across the last closed flux surface to the net production in the scrape-off layer. And this becomes an interesting way of addressing the question of how important is the spreading. This is like what we did in our first paper, but we put it in terms of gamma, which is, I think, inferior. Obviously, R sub A small means the turbulence is locally driven. R sub A large means it's spreading driven. And you can measure all these by Langmuir probes. And this expression is very likely a lower bound because you could imagine keeping other things in production, all of which would be damping, and that would just make the denominator smaller and the total value larger. So here's the answer. So we have it's a busy slide. So we have a histogram of the number of shots versus R sub A, the production ratio. And we have a plot of the heat load width versus R sub A. And then we have a plot of the heat load width versus magnitude R sub A by groups of points. So let's start with the histogram. So most, there's obviously a lump of points in 0 to 1, which point toward local production, but most of the points are not local production. They're at RA larger than 1. There's some very large values of RA noticed out here on the tail. These points around the 0 to 1 range, they are associated with the black triangles, the strong E cross B shear, which maybe explains why the local production is winning there. But there's some interesting questions. There's a broad range of RA values, and there are a few negative values indicating inward spreading. I mean, I don't understand this, but it's certainly possible. And there are cases where you might expect inward spreading. I don't here, but I mean, if nothing else, this should convince you we didn't cheat. If you look at the production, the heat load width versus production ratio, heat load for most of the classes of points, the heat load width tends to expand with the production ratio. Again, the black diamonds are, at lower production ratio and also lower heat load width. And working by groups, I think this one is a little clearer. So the question is, what the hell is going on? And in particular, can you understand sort of this batch of results here and these outliers out here? So obviously the ones with weak production ratio, you look, the shear is the prime suspect. So the low values in the production ratio seem to be associated with stronger values of shear, but it's not trivial because the production ratio is the ratio of two transport quantities, right? It's the ratio of the flux of turbulence energy to this integrated particle flux, and one would expect shear to do a number on both of them. But what the results are telling you is it does a number on one much more intensively than the other. So, and if you look at that in the spreading, the effect of the weak to strong shear, you know, is, well, it's more than an order of magnitude in the magnitude of the spreading. The effect from weak to strong shear is a factor of 2 or 3 in the flux. So, I mean, the spreading flux is significantly more sensitive to the shear than the transport flux. And one could interpret this as largely a consequence of the triplet versus quadratic, having more sensitive phase structures. But this is something still needs to be thought about. What's going on at large production ratio? The obvious suspect is the blob, right, particularly. So how do you test for that? Well, out comes conditional averaging. Now, so what you do is, you know, again, what's a blob? At an engineering level, what you might do is you define all fluctuations larger than some factor, usually 2 or 3 of the RMS value, as being a blob. Okay, and that's obviously not satisfactory. We can come back to that later. But in practice, this is what's done. So you can do conditional averaging, set a threshold, and go and compute, you know, R sub A and the flux, et cetera, with the conditionally averaged quantities. And in particular, you can compute the fraction of any of the fluxes carried by the blob to the total flux just by comparing the conditionally averaged flux to the total flux. And, well, surprise, I mean, as you go further into a blob-dominated regime, you know, as parameterized by a higher ratio of the conditionally averaged flux to the total flux, the production ratio rises. So that's the cases of high production ratio are kind of blob-dominated regimes. The shearing case, the shear-dominated case, has with low production ratio is effectively has very little blob contribution. And you can do this for production ratio or heat load width, et cetera, et cetera. So these large RA outlier cases are basically dominated by blobs, right? And it's effectively your spreading is blob injection into the scrape-off layer. If you plot the blob fraction versus E cross B shear, it of course drops. And by the way, that's consistent with one of the more important experimental works back in 2003 by Jose Boedo, where the blob behavior first was studied. So you can also look at the lambda Q versus the spreading rate, form a rate out of the spreading and versus the shearing rate. And a higher spreading rate is a broader heat load, and the stronger shear reduces the spreading rate. So all of that works. So what's the message of this? So there is significant, mostly outward spreading measured at the last closed flux surface. Okay, and this spreading is important. You can define this production ratio goody, and in most of the cases, it is larger than 1. And it says that the spreading is the dominant player in the scrape-off layer energetics. Okay. And the story of the local diffusivity, et cetera, that I mentioned earlier and you heard earlier, I think is conventional wisdom that is little more than convention, as the good Dr. Galbraith said many years ago. E cross B shear reduces the production ratio, and it does seem the spreading is more sensitive to E cross B shear than the transport. And high production ratios usually are a signal that you have blob-dominated dynamics. And certainly how you calculate anything in that regime is a bit of a challenge. So now, having kind of established that the spreading idea works, one wants to go back to the problem at hand, that has been created by Professor Goldston, and to look at how you could broaden the scrape-off layer by exploiting spreading from a turbulent pedestal. Okay. So this becomes a theoretical exercise, right? So it's basically a question of how do you calculate the penetration depth. By the way, this was done with Shu and Jibin Glow. And very important thing is, of course, how much turbulence in the pedestal do you need to get sufficient broadening of the scrape-off layer with? And what is the impact of the barrier on the spreading mechanism? Okay, that of course is a key. In some sense, the spreading has to punch through, and this is, I think, a step toward answering the question of can the soul broadening and good confinement be reconciled in some sense, right? You know, you can broaden the soul if you go back to L mode, right? I mean, so the question is, can you broaden the soul with a somewhat more tolerable fluctuation intensity in the pedestal? And all these, these I mode and WP, QHM and all these, acronym STU stuff, these are all, the game is the turbulent pedestal. And I made this comment. So the first thing is, look at just to double check, look at the standard models, as it were. And I mean, if you were going to look at the drift interchange with the sheath boundary conditions, those weren't mentioned. They're important. And E cross B shear. And so this is a standard crank. So that's sort of like the Myra Krashenikov paper. And you can plot the growth rates versus lambda over lambda heuristic drift. And I mean, you see in the regime of 1 or 2, they're all negative. And it's in some cases strongly negative. So everything's stable there as we were established. So the thinking then is sort of, the idea of a box, 2 boxes, and 1 box of the pedestal, 1 box of the soul. Can you calculate the penetration from 1 box into the other box? Okay, so simple enough in principle. So if you're going to calculate the width of the stable soul for a fluid particle, you can write down a Langevin equation. dr dt is the drift velocity plus a fluctuating velocity that you might associate with turbulence. You also have to realize that the dwell time in the soul constrains the excursion. Calculate the mean square step size. So you get V drift squared tau parallel squared. And this is just lambda HD 1 more time. And you also get a contribution proportional to the intensity of the fluctuations, the correlation time, and the parallel, transit time, the lifetime. You realize the correlation time, in principle, it could be shorter than tau parallel, but then we wouldn't be having this discussion because you'd have a strongly turbulent soul and the game would be won. In practice, though, the correlation time can never be longer than tau parallel because then it's just advected through the system. So in the end, you have delta squared is lambda HD squared plus the energy times tau parallel squared. So that gives you then the total soul width with the effects adding in quadrature, and the soul width is then proportional to the energy of the turbulence. Okay, and then of course you have to explain where that comes from. And this, of course, reduces in the zero turbulence limit precisely to what it must to the heuristic drift model. So for the turbulence, out comes the K epsilon type model again. But I mean, this is theoretical exercise. We'll talk some more about that, about doing better than this later. So you have the time rate of change of energy, the local growth, which is negative, and you can bury all the contributions from shearing in the sheath in the growth. The growth rate is negative. You have nonlinear transfer, and the transfer is parameterized by a parameter and an exponent for the type of interaction. And you have very important, the divergence of an energy flux, which is the spreading or turbulence energy flux. And one thing you want to do, you can't entirely, but as far as you can, you want to avoid making a Fickian closure of the energy flux. And I'll talk more about that later in the talk, but the Fickian model of the energy flux is just garbage. And that's something that's emerging later. But so far, we don't have to do that. You just write it as a divergence of an energy flux. And you can sort of gussy this up for, you know, more elaborate things. You just integrate that equation and take the layer average, and you get an expression relating the separatrix energy flux and the growth or production in the scrape-off layer, which is actually negative to the nonlinear saturation. So it's very nice that really the spreading is characterized by a single parameter, the flux of energy through the scrape-off layer. So it's a single parameter characterizing the spreading. So for gamma negative, you get a nice little balance condition in stationary state of the incoming energy from the scrape-off layer balancing the damping and the nonlinear dissipation, right? So that gives you and the second equation, you need two equations, one for energy and one for layer width, and that gives you the second equation. So the package deal is just this, right? So you have two equations for the energy and the layer width coupled with, well, what inputs? The inputs of the geometry is buried in the damping. There's the spreading influx, and then of course there you do have to build some kind of model of the nonlinear saturation. Now, I think the biggest swindle in this is, of course, the idea of a steady influx rate in the spreading. I mean, you would normally expect fluctuations here to be order unity, right? So gamma twiddle of order gamma. And that, of course, starts to point, should we be thinking more in terms of spreading as an avalanching process, which is the last part of this talk. So some of our old friends will come out again at that part of the discussion, but let's continue along here. I mean, so you can make a plot, start making plots of lambda over lambda heuristic drift versus the spreading influx rate. And the blue curve is the relevant one. I mean, and you get, well, it's interesting. You have two branches, right? You have a very weak turbulence branch where the damping is balancing the spreading, and a stronger branch where the nonlinear dissipation is balancing the gamma, the spreading, and there's a crossover between the two. The weak broadening regime is sort of shear dominated. The strong broadening regime is nonlinear damping dominated. The crossover is occurring roughly at where V tilde squared is of order V drift squared. So it's certainly clear that the soul width can be broadened due to spreading. So we have an experiment already partly done, but only just recently, so I can't tell you about any results, but that Jose is doing on D3D to look at this. And in the mini proposal meeting, always a delight to discuss the experiment. You know, Tony Leonard pointed out, so, which is fair, he says, you're never going to see the crossover. The best you can, you're going to see is you might get one asymptotic regime and you'll get the other regime because you'll recover Goldston if you go to a sufficiently high quality H mode. So really the problem is going to look like a bifurcation. You'll see the two branches, but you'll never be able to connect it, which I think is probably a fair comment in reality. So then there's the second half of the problem, which is what kind of pedestal turbulence do you need to actually produce this gamma E thing, this input parameter? And here things get dicier. So we looked at two limits. This gets into name your favorite pedestal mode. So we looked at two limits. One was collisional drift waves, and one would be ballooning, with the idea of Grassi-Elms. But we took special care to look at the E cross B shear layer effects, because this spreading has to penetrate the barrier. Barrier permeability to spreading is a key question. There was some studies of that by Wei-Xing Wang in the past, but well, there are questions to be asked. So, we estimated the spreading flux. Here you had to use the Fickian model, but we at least, for the correlation time, considered the shearing in the correlation time, right? So tau C is where the barrier permeability issue is buried. And to deal with that, we're back to Kubo, the Kubo formula one more time with the E cross B shear. Omega shear is the E cross B shear and the barrier. This would have been an old story in the first festival. Then you relate the E cross B shear to the pedestal structure by radial force balance. So you can relate omega shear to W ped and all of that, and crank away merrily. And you, of course, need gamma E0 bigger than the minimum to get any broadening, etc. And you end up with another curve like this. And the blue curve is the relevant one. So for E phi over T in the pedestal, around 0.03, 0.04, you can start to achieve a crossover into a kind of a more strongly broadened regime. All is not wine and roses, because that would just be the crossover. And, speaking of D3D, Richard Buttery is of the opinion that the scrape-off layer width as advertised for ITER is in fact 10 times too small of what it should be for proper performance. You can find that on Twitter if you go looking. He's on the record. So that's another little commentary on last night's song and dance. But so, there, if you really want to go up on this curve, you're going to maybe be facing rather more intense turbulence in the pedestal. And whether that all works, I don't know. We could look at the scalings. The scalings are favorable, right? At the base, the scaling parameter is rho over big R to square root. So that's, of course, that bigger is better holds true, but only as a square root. And also larger field works better. You might ask, where's the pedestal width? Well, it's there, but very weak dependence. It tends to drop out because it plays in the drive for the density gradient, and it plays in the E cross B shear, and the two cancel. So you can also go to ballooning. And here, the idea is looking at Grassi-Elms. And here you want to express the answer in terms of deviation from marginality. So in other words, how far does LP crit over LP have to be from 1? And you do a little arithmetic, and you again, the supercriticality scales with rho over big R and beta toroidal. So, the scaling The scaling is somewhat optimistic. It's interesting. So it is perhaps, when one gets there, all will be well. But I think one had better understand the road there better than we do at the moment. We also did sensitivity studies. In other words, there's obviously a lot of approximations in all this. The question comes up, which ones matter the most? And the issue of the crossover in the intensity is determined primarily by the linear damping. The slope in the asymptotic regime is determined by the nonlinear saturation. So that was at least a positive outcome. So, broadening works. What one needs is further and more quantitative analysis. I don't understand why all the great and glorious codes, instead of just making color pictures, can't produce analyses like this. But, I guess color pictures sell. So what's the broader messages? Turbulence spreading is important, even dominant process setting the soul with. The flux in of the turbulence energy from the pedestal, from the core, into the pedestal into the soul is a critical element. The production ratio merits further study and characterization. It also says spreading must be an important saturation mechanism for pedestal turbulence, right? Simulations should stress the calculation and characterization of the turbulence energy flux over flow visualizations and front propagation studies. One thing I did do in the last month or so is dig up all the people who did these studies of spreading. And I asked them, have you, tested, particularly this Fickian ansatz thing? Have you tested that at all with the simulation data? And the answer is no. Okay, so that's, I think, a festering sore. And we'll come to that in a minute. But it does seem that turbulent pedestal states are attractive for heat load management. So just you guys doing, the real men doing gyrokinetics, how about calculating the phase-space density spreading flux, which would be, I think, an interesting item. The experiments are necessarily local. So, I mean, we need the simulations to interpolate between local and flux surface average. And finally, Professor Goldston is back. And Professor Goldston points out when you go to high density in the conductive scrape-off, conduction-dominated scrape-off layer, you broaden enough that you may, at high density, basically, density goes up, chi goes down, layer broadens. You broaden the layer enough that you turn off the E cross B stabilization and the scrape-off layer can go unstable again. And that could lead to invasion of turbulence from the soul into the core. And this is his sort of little scenario for the H-mode density limit, which George did not talk about the HDL yesterday, but that's probably the more important problem. And I like to call this the case of the tail wagging the dog, right? And and then of course, there's an interesting problem. You could in fact have counter-propagating fronts and all. And this is a topic that is just speculated on. So go to the last part. This is the part that you normally begin with in the festival, is on kind of the general perspective on the physics. And there is a message, right? I think the focus on reality forces you to think harder about some of these generalities. So spreading, of course, is a classic, and they don't call it spreading, but in fluid mechanics, I mean, probably, at least from my experience teaching fluid mechanics, one of the 3 or 4 critical examples in the course is the turbulent wake, right? And it's important because it illustrates that going from inviscid to viscous flow makes a difference in the global structure of the solution, right? Not just the boundary layer, but by bringing viscosity, you form the wake, and then actually the potential flow far from the object goes from a dipole to a monopole. In some sense, you can think of the wake as a little bit similar to radiation in the far field. So that's a classic example in fluids that you always have to give, and you can use mixing length and similarity theory to calculate the spreading of the turbulent wake. It's a well-known result. And this then, of course, spreading is fundamental to these K epsilon type models, because in the part of the expansion of the turbulence regime is simply the spreading process. And what you usually get, and which is, the names of the guilty parties in this field, many of whom are in the room, are here, and you would, in the best French revolutionary tradition, you would need a large basket to accommodate all the business. What you usually get is a nonlinear diffusion equation, sort of like it's a reaction diffusion, and the only subtlety is the diffusion is nonlinear. And a lot of stuff is fits shoehorned into this form. And this also appears in these Bly's, Baumforth, Llewellyn Smith, and Young layering models, and in these one-dimensional LH transition models. They're all variations of these reaction diffusion games with a nonlinear diffusion. And by the way, the unwritten hope is that the diffusion in the reaction diffusion is going to be basically the same as like the chi-I, et cetera, in the transport. It's not going to be radically different. This is not a new question. Anyway, this leads down the road to viewing spreading as front propagation. Games like Fisher fronts. And again, these are all based on the Fickian model, and the simulations never check this. Okay, right, we went through that with Wei-Xing, and I also talked with Jae-Min and Su-Min Yi about a month ago at the same time. It's an interesting hole in the analysis. It turns out this is not exactly a new idea. So we're almost back to Alain's talk of the, we have a golden oldie, right, from Procroy-Sack, even with Sir Geoffrey Taylor. He's the communicator. So actually Townsend in 1949 was quite interested in this question of if you build a mixing model for momentum transport, can you use the mixing model to describe fluctuation energy transport? And the application that he chose, you can see, is momentum and energy diffusion in the turbulent wake of a cylinder. It's exactly the wake problem. And this, of course, is an old classic. You can see the yellowing paper. It gives you the air of, decaying empire, et cetera, et cetera. So, quite authentic. And he starts to make a number of interesting observations. He observed the wake expansion, of course, was not by a diffusive mixing process, but as due to a set of jets of expanding fluid, which was almost like avalanches long before the word avalanches came into being. And comments that could be translated as departure from mean field theory. But the thing I enjoyed most, he does talk about, the Fickian model, the usual thing, the mixing model for the Reynolds stress, and then looks at the Fickian model for the energy flux, right? This is the same game we're so proud of ourselves for having invented, and it was only about 50 years behind it. And the conclusion from looking at the data and so forth is it must be concluded that the use of a diffusion coefficient to describe the transport of turbulent energy is not justified, and turbulent diffusion, energy diffusion is a process independent of momentum diffusion, which struck me, very much in the spirit of the Predeman-Kaw comment. It goes further. You don't only talk about what you don't understand, you realize you do understand enough to say that some of your old papers would be better served for use in the bathroom, I think. So we also then actually started to look at some modern experiments, and this was done by King Long at SWIP, and trying to look at HO2A data to explore the relation of the intensity flux to the intensity gradient in the edge. And actually motivated by Townsend, she defined a kind of a density jet profile, which is simply the triplet V radial n tilde squared divided by n tilde squared, which is effectively the same thing Townsend looked at. And this case, and this is limited, it's developing, but this has always been the spirit in the festival. You have a case where you have not much of an intensity gradient, a slight one, but not much. And you have a very definite intensity flux. And it's about a little more than a correlation length across. So if you look then at the Fickian model, of course, you're dead, right? I mean, if you try to calculate the diffusivity of intensity, you just get garbage because you're dividing this effectively by zero when you have a weak intensity gradient. So the practical utility of the Fickian model, I think, is dubious. I mean, so this little data, little result, I think, echoes Townsend quite strongly. But go a little further to something that's interesting, is that we looked at the mean jet velocity, again, this quantity V radial n twiddle squared over n twiddle squared versus the skewness. You remember the story of, we're back to the Wa-Cardar and also the blob experiments of excesses go out and voids go in, okay? Well, interestingly, the jet velocity tends to be positive when the skewness is positive and tends to be negative when the skewness is negative. So the jet velocity skewness trend seems to follow the joint reflection symmetry relation and suggests that the spreading process may be better thought of, well, I mean, if you have a Russian accent, you might say blobs or voids, or if otherwise, you might think of it in terms of avalanches and voids, excesses and depletions going in opposite direction. So that makes one start thinking, are there better ways of playing this game? And so this is heading toward trying to describe spreading in terms of intensity pulses. So the first thing is edge turbulence to me seems always intermittent. I mean, if you have strong shear, then you're in a marginal avalanching state. You always have avalanches when you're near marginal stability. That's the best place to get them. And if you go to weak shear, then you get these strong structures, blobs. So the character of the intermittency changes, but the turbulence is virtually always intermittent. So it seems that pulses on avalanches are a natural description. So you remember the sort of thing from sand piles and self-organized criticality of looking at the deviation of the pulse from criticality, which is kind of related to the gradient excursion. And you just realize deviation, say, in pressure or temperature would have a footprint in the intensity and be accompanied by a deviation in the intensity. So then you play the sort of games we played with with avalanches now for these intensity pulses. So you know what's coming. Burgers is on the grill, as it were. I was getting close to 4th of July when I was writing this. So, but there's some new toppings on the burger. You know, it becomes really a whopper. And, so first of all, in the scrape-off layer, you're largely going to have delta E positive. So you have turbulence injected into the sole, positive intensity fluctuation. You'll have the mean drift. We can't escape Professor Goldston here. But very importantly, you will no longer have a conserved order parameter, which is one of the rallying cries of the Wa-Cardar business, right? The conserved order parameter. And that, of course, is just flat not true in the soul because you have an open system. The stuff just runs along the field line and out. So there is a damping, a local damping due to finite dwell time. The noise would be the boundary excitation. So rather than dropping sand on the pile, you just drive the system. So bingo, you have a kind of modified Burgers game, which you have drift, you have steepening and propagation, you have some regularization, and you have a dwell time decay. If you look at some limits, in the limit of weak fluctuations, of course, the only things that survive are the drift and the dwell time, and you get the lambda HD scale emerging. For the turbulence to matter, you need a critical size on the intensity pulse to beat the drift, and that's just that mock-up. That's sort of like what we were calculating before. So looks quite promising. Now, the structure is one of Burgers plus a Crook model, which you might call crooked Burgers, kind of like what you get in Moscow these days at former McDonald's. And this has an interesting feature as well, as you learned in your elementary PDE class, probably Professor Hughes taught you, these things can shock, right? And there's an interesting condition for shocking, which is, of course, the initial steepening has to be strong enough to overcome the damping, the Crook damping, right? And that gives you a condition for the formation of a pulse. If you don't meet that condition is the initial slope has to be large enough to beat the damping at the rate 1/tau. It's a simple exercise for solution by characteristics. And if you meet that criterion, you form a pulse and off you go. If you don't, it just goes right. So where does that leave us? It leaves us, this becomes a kind of a pulse formation criterion for propagating pulses in the scrape-off layer. And this would be basically determined by the strength of the intensity gradient at the separatrix would have to be sufficiently large. And of course, as the pulses propagate, they would necessarily spread out. And when they spread below the level set by the drift, you would have a de facto evaporation criterion on the pulse. And the time it takes to hit that point would define the effective penetration depth of the pulse. So it seems where this is going is to try to relate the statistics of the pulses and the penetration depth in terms of the statistics of the boundary excitations. And this becomes, I think, a somewhat more interesting way of looking at the scrape-off layer problem. One thing that's missing is the shear. And in our old, that's the part of our old paper that in fact, did consider the shear in make a kind of two-dimensional Burgers-like structure with shocking only in one dimension, but shearing in the other to limit the lifetime of the structure. By the way, there's a typo. I don't have the parallel, the constant damping rate here, but one could play the same game here. And then, of course, you would be specifying the excitation in terms of the perturbations on the boundary as a function of time and as a function of location in Y. And then shearing and scattering will couple the shear profile to the dynamics, and you can go off from there. So you would have a double Burgers problem, and that's sort of, I mean, the extent. That's just a kind of a little speculation to leave you with at the end. So finally, where's Nigel? You remember the Goldenfeld's Rosenbluth lecture in 2017, he pointed out, fundamentally, spreading is a directed percolation process. That's the most fundamental way of looking at what's going on. And that directed percolation is just percolation with a sense of times arrow. And I can talk a little bit about percolation in the afternoon lecture. These games with avalanches are, of course, just variations on the theme of directed percolation. And you may remember the Bachtang-Wiesenfeld paper of '87 really interpreted the self-organized criticality state in terms of a set of percolation clusters and stability to addition of a single grain. The mean field models of directed percolation all end up in terms of these hydrodynamic and souped up reaction diffusion type models that we've been talking about. If you want to really look at sort of criticality to spreading, though, you must enter a fluctuation dominated regime where some of these games aren't going to work. And that, of course, requires renormalization group analysis, which is beyond the scope of this discussion. I mean, it's not clear that we need quite to face that point in the fusion problem, but if you want to really understand the problem, I think that's where you have to go. So in terms of some philosophy, on that score, the magnetic fusion questions that we've talked about are within reach in the near future. I mean, there's great attention to the lambda Q problem. Other people know about it, even if Becquelet doesn't. And this attention is very much in the spirit of the good Dr. Johnson. I mean, it's a make or break problem. And there are several experiments going on D3D right now, and I know others. It is unreasonable for tokamak experiments to probe the critical dynamics to elucidate the basic questions. I don't know why the simulations haven't, but they seem more interested in making color pictures. So what we really need in this is and I've been trying to get George's attention on this, is a well-diagnosed basic experiment with some relevant features, something like the tube experiments of CSDX to study turbulence spreading and to look at it at a very fundamental level. It's quite challenging because of the range of scales that's needed. And I think the possibility for us, the road forward, is to write a proposal to LAPD, the large tube at UCLA, which is maybe big enough to support a sufficiently large dynamic range. So that's sort of in the offing for us. But I think to make progress on some of these fundamental questions, you need something to keep the simulations honest. Okay, and that points toward a basic experiment. And I see the Legion is about ready to march, and that's the end. So thank you very much. Can't hear you.
I like the connection to the earlier art or the context. The spreading of the those factors. The turbulence is of course straddle the gradients. Right? So you have basically really short scale turbulence and you have these avalanches that it's figures that actually connect all the way from the distance to the straight. And they are subject to shear to some extent, but there's also entrainment effects because it's a non-local form in your shear going both directions. So how could you incorporate these different scale disparities in the
What I would do is I would jump the idea of the solar model, try to make the model of the pedestal, what I was saying to the value of A, with the model of the pedestal of the soul, where effectively the soul would become a beach pedestal, and you can generate the pulses in the soul, wash out, break onto the beach, and be diverted away. That's really what needs to be done. I mean, that there are attempts at doing that in simulations. Seeing that, see the results, right? Kind of clarify that. But I mean, clearly, you have this picture of an avalanche initially. So, it's a question in the sense, how far does it wash up on the beach?
right? So yeah, I think the simulations can look at to spread a little bit. We start with the direction with the broad spectrum of turbulence. So maybe we can gradually increase the gradient changes the non-local dynamic.
And the beach would continue with the beach, it would have a rip current, right, which is the shear, right?
Yeah, because the shear is really it's very different.
The shear plays on both sides of the boundary. Because on the inside, it's the conventional, song and dance to get yada yada yada. At the outside, it just creates this, this kind of shear sitting there that basically wipes out the locally generated turbulence in the straight line flare.
It's challenging the basic experiments of course get away from that.
Well, I look at the basic experiment not as a simulation for tokamak, but as a laboratory experiment. The 6 of training is important. There's been a lot of studies study the achievements, right? Study, but in terms of basic studies of applications. And I think the way you make progress is you have the simulation and the experiment. The experiment keeps the simulation.
So in transition from direct to acceleration, how do you have that? Lifetime to how it scales and what's this.
So in the simple model, you can do it. I think in the experiment, and not the experiment, the simulation, you have to do though a simulation that devoted to addressing that and not devoted to coming up with a favorable number for clear.
But there's, I mean, because of the scale, it happens very easily. That's why it's that's a lot more than the reality.
things to try. Not enough time. Has to pay the bills. Well, he's got, he's trying to do an RG calculation, an RG calculation of the onset of the overlap of the slugs. Right. Tight flow. Yeah. So he's, after he solves that.
Moment. Turbulence spreading
I can't hear you, Norman. I'll come over and visit you. That's the idea. Yeah.
Turbulence spreading scale. So, for example, scale specific. In that case, speaking about
You don't have to speak about it.
but then with the spreads.
Well, there are a couple of, it's a good question there. I always like, I think it's so one possibility is the turbulence middles away at the base, which is kind of like the scale, small ends sort of eroding. The other possibility is that at the interface or region, something like a large distortion, but just overturns, and that's an engulfing. Different types of boundary layers and just different types of interfaces. So there isn't a unique answer to your question.
What proceeding younger one that is producing turbulence in the diverter really wrong?
It's not spreading, you just propagate wave. You could, but what happens if the stuff hits the separatrix? What happens then? Aren't you going to erode the? What do you want to do with that? I mean,
I think there was this idea by this Russian guy, he was proposing
Yukov?
Yes, propagating the producing kind of
You mean the idea? Is it the idea to have some sort of crosswind near the book?
I think so.
This, yeah, that. I don't know. I haven't thought of that.
Okay, so what related question or comment? Have you thought about how magnetic fluctuation or MHD can induce further turbulence spreading and so people are into the problem? You must have seen the work by M. Kobayashi and Ida.
Oh,
And
you mean the thing that just came out?
Yeah.
Yeah, sure. We have them on in our Kikuchi series this year.
So what field? So,
Well, I mean,
physical.
physics, the way, first of all, what they say is that the stochastic field modifies the ion temperature and pressure profiles that modifies the electric field that then allows the spread. That's their statement. And, whether you get the magnetic perturbation from MHD or some RMP thing or something is irrelevant. I wrote to them and I said, hey, look, gentlemen, why doesn't the magnetic perturbation dephase the two components in the Reynolds stress, the VR and theta? Okay, and then that would knock out the shear layer and thus allow the spreading to occur. And they didn't have a good answer to that.
I like your physics part of the personal work. Wouldn't that be a kind of useful actuator in fusion related, fusion relevant classes?
Like magnetics.
Yeah.
It's a question. I would see, if you remember Samantha's PhD, right? You could use the RMP as a phase decorrelator in the Reynolds stress. So again, if you're willing to tolerate a little less shear flow, what you could do is you could turn up the magnetics, decorrelate the Reynolds stress components, and weaken the shear and allow more of an invasion. And you would have a knob on the barrier by the magnetics, say by the RMP.
It would be very useful to say LHV.
Yeah, I mean, there's a no free lunch though. And as I said, the no free lunch is that you must pay for that control with some confinement data.
Oh, of course, but you have to pay too.
Yeah, I'm not paying anything.
These Chinese told me, you also pay.
I pay in labor. Yeah.
Maybe just David just afterwards, but just a remark: if you have those magnetic fluctuations, would you not expect that they act differently on the V tildes and the P tildes, meaning
Of
that
course.
so you could still get a drive for the flow through the.
And I mean, and there's also the story of our friend Shu, right? You're thinking along the same lines as Shu, ultimately, looking at the effect of both an electron heat load and an ion heat load, and the electron heat load becomes quite sensitive to magnetic perturbations.
David?
So,
David.
Which David? Oh, the crown. Oh, I thought. Has to return to the crown.
Just a comment, as a man who loves an analogy, at some level there's a lot of common ground in what we're talking about, and the tactile.
Yes.
You have the shear, you have the convective tunneling, magnetic layer, shear. Quite a lot. Probably nothing tactile is going to help. Conversely, you might be able to say something about that.
Well, I mean, I think the key penetration test that is in analogy. There's some simulation results on that, which would be you could learn something about. I don't. How much theory is it? I think not much.
one simple question from Christopher.
This movement is faster.
So I just have one simple question. So according to the Broadening have an extrapolation for the size of either machine, which is 1 millimeter, so which is about
If that, yeah.
and your model, the turbulence is spreading. There's a direction from our sphere, so which
large size for the leader. So you show some breadth, the lambda cube. Do you have any idea of this calculation we apply this model to
Well, I mean, I think what I'd rather do is keep maybe what the symbols mean, and you can play with the numbers. That's, I mean, I think the issue is what is the figure of merit? If the figure of merit is to make the crossover, in other words, to beat ghosts, then perfect. But what I was saying, it seems to me you need to be more than beat ghosts. You need to transfer. That you know, you're gonna need stronger turbulence levels. It's not a yes, no, it's a sort of excuse me, cost benefit analysis.
So on the subject of turbulence, and I'm thinking from hydrodynamic limits, maybe, so it could be completely irrelevant, but we know that if you have a boundary layer, that you have extreme events, bursting events that take place that have energy levels, local energy densities that are much higher than an average sort of prediction based on just statistics of fluctuations. Do you take this into account when you're, at the level of building a fusion device where you have to maybe worry about these events? Do we have a control over what the most extreme event can be, especially when you're trying to push the turbulence up to a high level? Are you actually reaching a risk that something could happen?
I am not aware of any risk analysis of that sort.
I know it's been a popular area now in the last, say, 10 years. Taking Freddie Boucher, other people,
Right.
looking at extreme events. And this is something that weather forecasting, climate modeling is another thing that people worry about. Weather prediction is an example of, extreme events can happen all the time. It's a regular thing. It's non-Gaussian.
There's a lot of emphasis on extreme events in the sense of large L's, large bursts, and also disruptions, which you can imagine what that's like. But in terms of like turbulence bursts, I've never heard that sort of thing propagate into machine design. I think that it's more like, can you get any turbulence at all and broaden the heat load?
But you did address some of it, maybe as a turbulence as a precursor for an element. So in
Yeah.
that sense,
But there's not a risk analysis, is what he's asking. Yes, of course, it's possible.
okay, last. Okay. Well,
Right. I don't know. I mean, I certainly don't see how it would benefit environment. I don't think it would hurt the environment. It seems, that is something I thought might get the attention of the locals. I mean, you guys. Yeah, okay, but I mean, you guys have been yelling about, and also La Bombard, the tail wag the dog experiment, right? Where you generate the parallel shear flow in the scrape off layer, and you generate some kind of inward propagation. So when I was preparing that, I was wondering, did these guys, when they did those, Jamie Gunn years ago, I recall, when they did those experiments, did they ever bother to measure the spreading flux of the separatrix? And I think an interesting experiment on those lines to be would be to repeat that experiment and then have a measurement of the spreading flux and see whether in fact it was going inward, right? And then, try to do causality, right? Turn it off and see if the spreading flux reverts. That doesn't sell on D3D, by the way. If we could do that experiment, we do it ourselves, but they don't want to hear that. The official position there is the dog wags the tail. Is the
Okay, well, last question is for me. So, as you know, the shear layer is also quite important to prevent stuff from getting in.
Yes.
And you mentioned the interesting idea, because you're connected to the wall, you will break some, the joint reflection symmetry, and you will pay
you'll break conserved order parameter.
Yeah. Or at least you might put an asymmetry between what comes in and what necessarily what comes out and what necessarily comes in. So a way of looking at things is how to promote this maximum asymmetry, because you want stuff to get out but not get in. Do you have any idea how you would promote that asymmetry? Playing, injecting either neutrals or making the stuff cold locally, or
Neutrals, people are playing with neutrals now to make barriers. You know that, right? That's the thing of MAST, right? They claim that they inject some neutrals and they get a kind of a front in V phi, and they get a shear, and bam, they claim you actually get an LH transition from neutral injection, which is a little. Jose is trying to do that as we speak, by the way. So that's a way that will contribute to barriers, so that will keep stuff out. But I don't know whether that's what you want. Right. I mean, are you trying to promote barriers, or?
No, to promote that asymmetry between
Oh, in other words, if you have the blob and void population, I mean, then
prevent the void getting in.
yeah, I think what you need to do there is you need to think about what structure electric field will kill one but not the other. I think that would be the thing I would look for, and I would start by revisiting Itamura Sensei, right, who was looking at electric field shear asymmetry effects in blobs and voids, and try and build on that. But I think then you'd need a control knob on the electric field in that region.
Well, it's been a long morning. Let's thank Pat again. And